Alright, so today we're going to be talking related to GPUs and how they're programmed. A lot of it kind of from a hardware perspective. I don't want to make this really only a programming class, although there are a lot of hardware software issues that become important to deal with. So I do want to deal with enough of it that you would feel comfortable going on to it. And then my suggestion is, right, this is a graduate level class, that you guys try to write and compile some program to do just some GPU programming, just to test it, to get you familiar with what's going on. So before I get into kind of the hardware and the programming of this, I want to kind of get in, there's a basic difference between what we do with a CPU and what we do with a coprocessor like a GPU. So everything we've dealt with up to now is what I would call kind of classic or old school type optimizations. I mean, even the lab area where we're going on and building it, you're building an out of order machine based on Tomasulo's, which actually comes from the 60s. So these are not new techniques, even though they're very solid and well used techniques. But they're all designed around the idea of latency. Latency becomes a big issue, and it's still an issue to me on the overall program area because that's used in scientific computing. You care about when you get your answer. And particularly when you're doing short iteration rounds and all kinds of stuff like that, you want to make sure you get through them. But contrary to what we've been doing on the other portions, when you do a GPU, GPUs are not optimized for latency. GPUs are optimized for throughput. Everything is designed around throughput optimization. And there are some big areas that become very crucial to this, and some areas where I say are kind of important to think about for the future of computing. Now, you will never go to an exclusive GPU machine. The idea is almost oxymoronic as it goes on. And I say that because in order to be able to handle them, a CPU is extremely general. So it can handle any type of control structure, and it does things very efficiently. And there's always portions of code that are going to be centered around that type of highly flexible area. Being able to interact with other devices and things of that sort. But when you take a look both at the speed up achievable and also the performance per watt. So when you get down to power issues, which, power, heat, all the rest, which is a crucial idea, nobody really competes dealing with a power basis with what you've got in GPUs. Right? Computation per watt is so much better on a GPU. It's, I believe about an order of magnitude almost better on it. It's significant. So when you want to go, to the exascale computing and things of that sort, it's going to have to be significantly based off of GPU type computation to achieve that performance level. But that performance is pushing into other areas because even embedded processors are getting into this. They've got, cell phones and tablets have GPU computation. They're not big units, but they are available. And processing those become, pretty crucial even in mobile computing. They also do them, believe it or not, there's a bunch going on into embedded systems even in like the automotive industry. Because you have like backup cameras, automatic braking cameras and things of that sort. How do you process quick enough to tell there is an object coming at me and I need to stop? And your traditional embedded unit is not going to be able to handle that. So GPUs are really important, and I'm willing to tolerate a latency increase inside them as long as I can handle it on a much larger scale throughput-wise. Now, by doing so, I can often, in the net, even if I make an individual command longer, I can make a sequence of commands shorter by optimizing throughput. And this is what I mean by it. On a traditional sequential one, let's say each of these little boxes is one command. So that I've got them going. Now, once you go to pipelining, this is how we attempt to achieve that same, so we have, so what I have, 6 of them. So you can see I can, still reduce with this level of parallelism, but that's a latency base, I haven't changed anything. Even if I slightly elongated it, wouldn't matter. When I go to a GPU, however, I'm trying to take all of these and run them, assuming they're compatible. So even if I lengthen these a bit, I still would be significantly shorter. So I can tolerate this taking slightly longer than it would up there in order to achieve them, yeah?
And there's such advantages, there's specific advantages and disadvantages to both.
Yes.
You foresee a day wherever they work together in terms of processing.
And that is basically what we do right now that's going on. You split them. If there's a sufficient area to get the advantage.
But I'm saying like more commonplace, because I'm sure for specific science applications, and because usually people use GPUs for graphics and,
Yes.
and CPUs for.
And if you take a look, and that's absolutely true. For graphics, it's king again because you've got a high throughput. And it's actually because it came out of that environment that goes on. If you figure your typical display, you've got at least 1,000 pixels by 1,000 pixels on average, right? I mean, maybe 1,700 or whatever. But you're on the 1,000 by 1,000, which means you're in the order of millions of pixels on a screen. That means if I'm doing the same calculation for each one, right? I have to calculate luminosity and maybe apply a texture, and right. So there's these series of operations that go on. But it's parallel on the order of millions, because I can separate each pixel as a separate calculation, and I'm doing the same exact thing to 1,000,000 of them, so it's very efficient to throw them at them and let them calculate. And what you're doing is you're calculating a ray trace, and then you're applying something. All of those are matrix operations that's going on, because you've got, some scene that's out there that you're, trying to figure out, and you've got a view frame, and that view frame has a, coordinate system, and, the person's looking through it. So all the things you're calculating, those can all be described as matrix transformations. Now, if you think about it, take this same stuff and apply it to, there have been people who took either my imaging or Kalman filtering type class in that. They're all matrix operations. So that same exact type of activity goes on. So scientific computing is pretty much one-to-one the same type of calculations as you would do inside graphics. As a matter of fact, computer graphics and robotics are indistinguishable mathematically, the types of problems that you solve, because it's still transforms of coordinate systems. So whether I'm doing it to look at stuff or to figure out where an end effector is going and act on it is pretty irrelevant to me as it is. So problems that fit into there are going to handle in a pretty nice way. Now, if you were to take a look at this and say, okay, does this work for everything? Well, if you're dealing with, like for instance, I cited cars and backup cameras, you're dealing with imaging, right? So therefore a computer graphics area. If you're taking a look at people, even in their everyday life though, people take all kinds of images and want to, have my friends automatically recognize and face tagged and all the rest, so facial recognition and all the rest of these, you're dealing with a huge number of problems. The one thing you want to, and we'll hopefully get more into this in a couple minutes, when you're dealing with GPUs is you've got to simplify the type of task that's going on, because they've got to get that parallelism. And in order to get a high level of parallelism, you have to make sure that you're not dealing with a lot of control. That everybody really needs to be running the exact same type of a thing. So control in this sense, we mean things like ifs and for loops and the rest. We've got to make sure everybody is running the same little section of code. And that includes like divergence, because I can fake things that go on. If inside my loop I just go if, and I have some condition A that's going on, else, some other section of code, you're really either running this section of code or this section of code that's going in. And if this is fairly common that could flip, that it's somewhere around 50-50, that means half your threads are going to be running here and half here. Well, therefore when running this one common code, really, you're running two different codes and you're just hiding it in your own mind. So we have to look at this and say, no, really that's divergent. as far as code goes in, they're not running the same sequence. You know, so this type of a control area is the type of thing we don't want to do, if possible, inside of a GPU. We really want that you're running this. You know, break it down so you're running this segment. And the CPU separating out whatever goes on. That doesn't mean I can't process those type of things, but you gotta say what's efficient. And that type of separation comes out. Now, why, you know, there are a lot of cases where this is done very efficiently that's going on, and it's happening more and more, but why doesn't it happen in every application that's out there? Where some of it is developers, you know, if they're dealing with a common application, they may not be aware of this level of programming or how you have to break it up. So part of what I want to do is make you aware of the thoughts of how you go about programming these. And then at a certain point, you're just going to have to try them. That's going on. That's why I say, you know, try some code, and there's some very simple ones you can do. But how it goes in. So there's the basic concern, you know, you can see I can improve latency for a group of commands by, even if I make the latency of an individual command worse, as long as I get a sufficiently large improvement in the throughput so that the aggregate sum then therefore is shorter in overall length. That's basically the trick. Now, in order to do this, there's kind of a basic sequence that's going on. So I've got a CPU, and that CPU is going to have access through, you know, some type of a bridge structure to RAM, which is your main host memory. And depending on how your structure goes in, we're going to assume that I can have my GPU sitting off this. So when you're actually running your standard bits of code, you compile, you load your code here, and it communicates to the RAM and off it goes. So that's kind of the basic structure. When the GPU has to get incorporated, now I've got to have a section of code running here, another section of code running here, and I have to be able to send it data that comes up this way and timing control sequences to say, run this particular kernel now, run it and get the answer back. And that becomes, so there's transfer that goes on, and there's transfer both of data and of control sequences. Start, when are you done, how do I know the time sequences that go in? So this is one of the first ones that we want to think on. As that goes in, right, I've got to be able to load in control instructions, load in data, and then offload data. And there is actually memory inside here. We'll deal with 3 different levels that goes on. Globals, shares, and then the local ones for the threads as they go in. At the moment, let's just deal with the highest, simplest one, which is the global memory, which is kind of your equivalent of RAM for the device that goes on. So I'm going to have to transfer a large block of data. Count that that's going to take you about a millisecond that's going in. So, yeah.
Is the large block the same as the page size? Or is it?
So it will probably be, depending on your data, a lot more than a page. So since scale-wise, there's kind of a joke that a GPU doesn't get up in the morning until there's at least 1,000 threads running, okay? So you're gonna want a pretty good scale on number of threads, but in order to keep it running, your biggest slowdown is actually on memory. And, we usually rate this based on what we call arithmetic intensity, which is basically if you take the number of operations you're going to do, all the floating point calculations, and you divide it by the amount of memory that you're utilizing, or access time, there's a couple different metrics people use, but basically taking, you know, computation that you have to do divided by the memory you're having to use, the bigger that is, the more arithmetic in essence, you know, the more dominated by computations. GPUs love arithmetic, they hate memory. So the stronger your arithmetic intensity, the better it goes. That means commensurately, you don't want to be doing a lot of memory transfers. Now what do you do when you do have a lot of memory that goes in? Well, a lot of times what you do is you'll load up a very large amount of memory, which will be many, many pages. and you'll start running some calculation, and then you'll start, while that's going, you can start loading in the memory for the next operation, so you kind of hide it. Right? Because I can be doing more than one thing at a time on a GPU. You know, so load memory, launch kernel, load a different kernel that's going to be following up's memory that's going on, get the answer back, launch that kernel, load your data back out from the first one. So that type of hiding allows me to do this type of action. Instead of doing, you know, load data, run kernel, offload data, load data, run kernel, offload data, right? That would be very inefficient. So we try to do this type of thing. Load data, run kernel, offload data, but while this one's running data, I'm loading data. And we can actually run more than one kernel at a time on a GPU as well. So as things, on very early stages of them, we couldn't. But at the moment, you can run multiple. If you look at a lot of videos that are out there, they'll tell you that the GPU cannot launch its own. That was probably true up to several years ago, but at the moment, GPUs can launch their own kernels, and there's actually, they can even initiate some memory transfers, which a lot of people say they can't. The newest generations can, so that they can do what's called DMA, direct memory access, so that you can actually request and send data as it goes. But the general principle saying that you really should try to restrict your memory as much as possible is important. That being said, memory is one of the biggest issues that comes on the throughput area and on transfers. And so a lot of the stuff that I'm doing, for instance, I'm trying to reconstruct the volume of some of these head, for instance. There's a lot of data that's just involved in calculating those proton paths and everything else. And so, you know, if I can preload the data and then just keep crunching it iteratively, I can get, you know, there'll be a big burst of memory, but then I'll get a lot of arithmetic intensity off of the subsections that I can go into trying to improve them. But how you do that becomes a really huge issue. Does that make sense? Right?
I
So,
have one other question.
Sure.
So since the GPU has to load, or since it prefers to load several pages of memory, does that mean that the time slices against each process is different than on the CPU? So when the CPU, so I guess, does the GPU and the CPU, they have to be synchronized when they load in and out processes?
So, depends on what you mean by synchronized on there. The clocks will be different, okay? So technically synchronos, right? Syn means with, chronos a clock, right? So if you have a synchronous operation, it means that they have a timing signal that's common between them in some sense. But that doesn't mean I technically have to have a shared clock. Your CPU is probably running, you know, like 2.6 gig or something like that. Your GPU is probably running closer to a gig. So it's a very different clock speed that's going on. But what you have is a common speed for your memory that's going on, and the CPU will initiate those memory transfers. It'll initiate the creation or allocation of the array on the GPU. It will initiate the transfer of the data into the GPU. It will initiate the GPU running its section of code operating on it, and it'll initiate the transfer back and eventually the deletion of that allocated variable as it goes in. So that's all on the CPU, but it'll do it as a timing signal being sent, where it'll send a control signal that's going in. And it's not a control signal that's running all the time, it's just a one-time signal that says, here, go allocate this, right? Initiate this data transfer. And this is where the direct memory access goes on. The CPU will send a command that says, here's the block of memory that I want you to transfer. And then you actually use the DMA protocol that goes on to actually transfer it. So it'll tell it there's a DMA control, and you'll say technically, you know, this is the block starting area, ending area, and it'll do the transfer that goes on to them. And that allows you to take advantage of as much bandwidth as you have. Now, to the programmer, you don't actually even see that that goes on. You just see, you know, I'm just moving this. And you set the device areas to whether you're transferring from host to device or the other way. Is that?
Yes.
Okay. All right. So just when you're breaking it up though, this is kind of my first thing to look at. You can actually go to a faster thing like a GPU and get worse performance. So when you're first looking to see, should I, right, I always say write it all on host first. And then look at the area. Do I have enough threads to make this interesting and efficient? Is there enough calculation in a thread that the time it's going to take to transfer the memory in and then transfer the answer back, is there enough calculation going on there that I can get the increase? Because you have to count that there's going to be the transfer to it, the calculation, and then the transfer back. And the calculation on the CPU has to be overall longer, right? Otherwise, there's no gain. So what most people do is they compare this, how long is the calculation going to take, to how long it'll take there. And then they take a look at the net performance, which is going to be based on that number, and then they wonder why they are not achieving everything that's out there. If you don't account for this when you're looking at, should I bother to offload this, you will get bad performance. And a decent number of people do this. This is kind of what happens inside of like MATLAB. If you just use MATLAB's area to do GPU, it will do that profile where you can, right, you'll do a little X for, you'll do a calculation, you do an X for transfer, calculation, transfer. Now, it's possible that some of the stuff you're transferring back and forth, you might actually be using the same amount, right? Because it's possible I'm operating on the same variables, maybe I'm iterating, first iteration, second iteration. So it could be the same value. So I might not need this at all. I might be able to just run it internally. Maybe all you're trying to do is check to see, you know, have I converged? Is my norm shrunk enough, or do I need to run another iteration of it? Well, I don't have to transfer the whole thing back to achieve that. So you have to think about where it goes. Now on MATLAB stuff, when it goes in, when you run it, since each command has been optimized to work that command on the GPU, to make it easier on you, they transfer, do the calculation, transfer back. Everything's back on the main area, so now those other commands don't have to fall through. Well, that means you'll be very fast on that speed, but you'll get this type of area on the transfers that'll kill you performance-wise. And this is why even on machines that can have, say, 2,500 threads running, you know, at the same exact instant, that doesn't even mean what's sitting in the background, that's actually being computed, that you can have that many stream processors. You know, because of this added area, you can actually get speed ups on MATLAB that are as impressive as, you know, 2 to 4. Even though, you know, sometimes they even get up to 18 or 20 on something that could get a speed up of 2,500. You know, and I mean, doubling your speed is still good, but it ain't that impressive. And the question is, why does it do so badly? And it's oftentimes has to do with these memory transfers because it's going back and forth unnecessarily. If you load a variable, calculate, put it back, load it back, calculate it, load it back, right? All those extra transfers can really gobble up all of your performance time. We call that sequence thunking. That's, you know, kind of the term that goes out there for it. When you keep doing this memory transfers back and forth, that's going on, and it will really kill your performance time. All right. Have you guys ever written any code on these before? Okay, so like any other compiled code that's out there, right? You can technically, in a lot of the examples you'll see will be Windows-based, so they stick them all in one file, right? And then what happens is NVIDIA has their own compiler, which is NVCC. And NVCC, so think of it as NVIDIA's C compiler that goes on. So that'll let you compile. It'll usually, you know, it'll separate the code out into what's the device code segments and what's the host code segments. It'll compile them separately, and then when you do the launches, it'll do the appropriate loads for you as you go. the basic sequence that you're gonna do inside that program, and, you know, like I said, you can separate these out, so, but assume this is one file, so I do the kind of cutoff corner, because it kind of looks like the page turn. So if you look on a lot of the icons, that's actually how you mark a text file. When you're doing them, you're gonna have kind of your regular C code stuff going in. Do you remember how you allocate memory inside of C, just on the host?
Malloc.
Malloc, okay? So our version is CUDA malloc. All one word, that makes it look like it's two. All right, so what do you need to know normally to allocate for a malloc?
The size of memory that you want and the data type.
Okay, so I need to know, in some sense, the amount of memory that I'm going to be allocating. And you also need a pointer, because it's got to answer back to you to say, where is it? Right? Because you've got this gigantic amount of RAM out there that's going on. Where in the RAM does it put it? Well, you know, when it creates a spot here, it's got to give you something that says this is where it's located. So the pointer gives you that starting location. And all it needs to do is give you the starting location, because you're going to tell it how much do you want. So that means you know the rest of it. If I tell you where it starts and you already knew how big it was, you therefore know everything you need to know about this. Now, technically malloc does not need to know what the data type is. All it's giving you is a block of memory. All right? Technically, you are the one who has to know how to access that one or wherever. You can access it in a wrong way. Now, what often is done on systems to make this nicer for you is they will let you specify it. But the reason why they do is, you know, if I know I want 1,000 double precision numbers, then I can take how many addresses per double precision times how many double precisions do I want, and I multiply them, and that'll give me the total size. Malloc doesn't care about that, right? Malloc just wants the overall number, but you can calculate that by just saying, you know, it's 8 bytes each times 1,000 of them, and that gives me the size that I'm going off of. Right? So malloc doesn't care. Now, for our NVIDIA system, there's two different areas that you're allocating. This, your traditional RAM, is right here that's going in. So if I have a pointer, it's an address inside here, and that pointer is just what's the starting memory address, right? So these ones are, you got a whole bunch of bytes in here, and they're numbered from 0 to whatever. Well, but I also have RAM over here that's on this, the GPU has its own little stream processors, and it has its own RAM. But that means these ones are not in the same address space as this is. This also has starting at a 0 address going on down. So I've got two different address spaces that use the same numbers. So I've got to keep them separate as they're going in. So just like we did before, when we do the CUDA malloc, I'm going to need to have the pointer just like you did before, and I'm going to need to know the size and so on, right? The important thing on this one that's underscored, and this is the most common mistake when people first start programming, is they use an address that's pointing here to point over here. You'll declare the pointer exactly the same, right? So if I want to have a pointer to double, right, I can just say, you know, that I'm going to do, you know, double, and then do the asterisk star, and then give it a name. And that tells me I've got a pointer to type double that's going on. But once I've made that thing, it means a pointer is just an address where doubles are stored that's going in. You know, I can use that pointer on a CUDA malloc, and it'll give me a number, which is an address. That number could be used either here or here. It only logically makes sense to use over here because that's where it's correctly pointing to something. I guess the best equivalent I could give to this, you know, if, you know, somebody gave you their address and they said, you know, my address is, you know, 1492, right? But I don't tell you the street name, right? 1492 on one street will be an address. It makes sense, it fits within the range. 1492 over here will be an address, it makes sense. You know, so there's no way you could just in advance say yes, no to it. But it will only be pointing at the thing you care about over here. So what we do to distinguish it is just a convention, a non-enforceable convention that when you define your pointer, if you're on the GPU, you give it D underscore and then whatever the pointer name is. D for device. If you're on the CPU, we go H underscore and then the pointer. And that means host. So you could technically name it whatever you want. You could put Aunt Matilda there as the name of the pointer. But if you follow this convention, you'll be able to easily recognize what was the space that that's in. It's kind of just giving you the street name in the variable. I'm just telling you which one is it on. Does that make sense? So you're going to first do a CUDA malloc. It looks basically like everybody else. My strong suggestion, most decent systems that are on here will actually give you kind of some, you know, base ones that are on there, and you can just copy and modify them. But you do a CUDA malloc, okay? Now, if I want to copy a block of memory inside of C, right? There's a command called memcopy, right? And it'll allow you to copy from one area in RAM to another if you want to do some block-to-block transfers and stuff. Well, we have the equivalent here, CUDA memcopy. Okay, and CUDA memcopy, just like our regular memcopy, allows me to copy from one block of RAM to another. Now, the question is, am I copying this way or this way? Well, you have to give a pointer to wherever your source and your destination is. You got to tell it how big is the transfer, and you've got to be able to say which direction is it going. Because when I'm first copying them over, I'm going from the host to the device, right? And then when I'm done my answer, I'm going back the other direction. So CUDA memcopy will be done on either side. That's going in, and for each one of these, you have the pointer to the destination, the pointer to the source, the size that you're doing, and then the direction that's going in. So on the first one, the destination is going to be a D underscore pointer because it's on the device. The source will be an H underscore. Size is however big the block is you're copying. And then to remember the direction, right? These are little code things. Remember we said nobody wants to remember, was it 0 was that direction, or 1 that right? What was the code sequence that told it which way to go? So we created pre-names for these. So there's command CUDA mem copy, you know, device to host. Device to host, and CUDA memcopy host to device. They're predefined values that just hold the correct direction for it, so you don't have to remember. The one thing that just is, it really is mem CPY, it's abbreviated. And they do camel case, so that's capitalized, device to H, right? But those stuff, I mean, my biggest thing is not worrying about syntax and those. I want you to understand the ideas and what to look for when you're reading on them. Because I think if you get the idea of them, it's easy enough to take a copy of code and modify them. But if you don't know why the heck they're doing it, this also kind of comes down to the area of how about next generation, if you get into building hardware or customizing this for things, how are you going to take advantage of it? So you've got the forward and backward, and I've left a spot in between for the kernel. And then, you know, I might at some point have to free up the memory. The final one that goes in is I have to be able to run my particular code sequence that goes on. Just like when you're calling any other thing, you have whatever the name is that's going in, the kernel you're invoking. But now, when I run that kernel that's going in, like say for instance I want to take a for loop that was running over and over again, like I was going to do for a specific thing, let's say we want to do vector addition, right? Just so we have a specific. And I want to calculate A plus B getting stuck into C for some vectors that's going in. And I say, great, so I might have a loop that's going to go, for I equals 0, I less than whatever n is, I plus plus. And then I want to say C I is equal to AI plus BI. So this is kind of your standard looking, thing to add up two vectors, stick them into a third. When you want to turn this into a kernel, for us, remember we can unroll loops, right? So we'll get into when we're invoking it here in a sec, but I want you to see where we're going to split this up, which will be a little bit weird. This tells me how many times I'm running. If you look at this, can you tell anything about how many times it runs? Does that tell you anything? Right? I mean, it tells you how they're interacting between. This is what tells how many times you run and all kinds of other stuff. So if I were unrolling this, I'd need to know this information. So there's kind of two pieces. How many times is it running? What happens at each individual iteration? Well, this one is going to take them and do this type of a sequence, right? Do one, then the next, and the next, and the next. What if I completely unrolled it and wanted to stick them all right next to each other in parallel? Well, that means I'd be doing all these, and I'd have, C0 equals A0 plus B0, and all the way down up to C n minus 1 equals A n minus 1 B n minus 1, right? I'd have all those in there. So at any particular one of these, the way you would characterize them is this. How you set up how many of these, that information you get from here. Does that make sense? So this is kind of the classic sequential. Well, what do I need to do to specify for running them inside a GPU? Well, what you're going to run is this interior part. So when we write the kernel, this is the part we have to handle. When you invoke it and call it, that's when you have to tell it how many of these are going to occur, right? And how it's going to get parallelized. So we do this kind of triple chevron, and I'm going to leave this over. This is just going to tell me kind of the how many to run, right? That how many to run is going to give me all the information I need that's related to this. It's going to actually give me more than just n. It's also going to give me how I'm going to split these across the stream processors and stuff. But, basically it's handling this level of information. And then inside the writing of the kernel, it's going to have this. So we're kind of separating your loop up into two portions. You can think of your iteration counts as going to come across here, inside this triple chevron. And it really is 3 chevrons around it. And then, just like anything else, I'll have the round parentheses and I can pass, individual little pointer bits that goes on. So any parameters that I want to send to it.
And the parameters can be within the scope of anything else that's in the program.
Yeah, imagine that, yeah, it's just, so those individual, but you shouldn't make them big vectors. But I can pass the pointer.
Okay.
So if a very common one to do is like, for instance, that D underscore pointer, if I want, so I might pass to it, the D underscore pointer for A, B, and C.
And so
That's going into it. Now I would have had to have pre-done the copy to copy A over, and I'd have to do a second CUDA memory copy to copy B into memory space. And then in the parameter areas, I would pass to it the pointer to A, the pointer to B, the pointer to C, and then afterwards, I'd CUDA memory copy C back into host memory. Does that make sense? So that's kind of where this goes, but think of this as small things, right? You're passing the parameter, right, which is just a couple things, so like the pointer, but I don't want to pass the entire vector, right? That would not be a good parameter pass, right? This is, whatever's going to go into that is going to go into local memory. And this is on the, we had to talk a little bit about how the device is kind of set up. But just for the moment, just think of this as going into small, fast stuff, right? And to make it small, fast, you better not make it a lot that's going. When you do these large copies here, this is going into global memory, and this is going into local. Now, you know, if you can say, hey, I can absolutely will have that space, goes on, yay. The other thing to remember about passing that pointers that go there, it's going to be copied to multiple locations. Because each one of those, since it's going local, each individual thread will have its own copy. So if you pass it to it something generic, like everybody needs to know where the pointer is. But if you do the copy here, they're all sharing one copy. You give them a pointer so everybody knows where it is. So it'd be kind of like saying, if I'm going to have a party at my house, and we all want to celebrate, we're all sharing one global resource, the space at my house where we're going to. Now how do I make sure everybody, well I give everybody an invitation with my address and directions of how to get, you know, we're going to have a pool party. So, you know, I give you directions, here's my address, you know, park on the driveway and just come right around to the back, right? So I give you directions, but everybody gets their own directions, right? So everybody gets their own local parameters that give them what they need to do to get to the shared resource. If, on the other hand, I were to put the pool party here, I'd be giving everybody a copy of my pool. So there'd be a whole bunch of different pools out there. And each one of you would have your own individual pool. And if you modified your pool, it wouldn't be the same as somebody else's pool. So it'd be like having a whole bunch of separate pool parties in identical looking spaces. That's not what you mean generally, okay? But I mean, maybe under a circumstance you do. You just have to understand what's the implication of doing that particular area. Does that make more sense? Okay. So, if you think about what's going on these ones, then the question is for these, how am I going to handle them? Okay? So let me get into a little detail on how the hardware looks, and then that'll let us lead into how we're going to program this. So how the hardware looks on the GPU. Have all of you seen GPU hardware before? I just want to know how far to go into detail. Okay. So here's the simple structure. Imagine this is my GPU. Off this GPU, I'm going to have kind of a central data bus that's going to go in. And this is where I'm going to get my transfers to and from the host and all kinds of nice stuff like that. So I've got a way to transfer them in. Right off my bus, I'm going to stick, pretty centrally located, a whole bunch of global data available to you. This is, just think of this, you know, as basically your RAM and everything else. So, you know, this is actually on the card. I'm not specifying internal to a chip. This is all card resources. So this is probably actually going to be separated off. But I want you to think of it as kind of close to the bus, right? So when you do use those CUDA MEM copies, it's going to come in, it's going to drop them into your globals. Okay? Now, I'm also going to have available to me a whole bunch of these kind of stream processors that go in. And any one of these particular ones is going to have a sequence of basic things. I'm going to have some shared memory available to them. Right? Now, the shared memory for this particular stream is different than the shared memory for this. When you go to run these, remember we said you could actually have multiple kernels running? So think of a kernel as in kind of like a cohesive group of threads, right? A thread being a particular process run that's going on, how it's going to handle something. Well, I could have one that's calculating one thing and something else calculating another. And these kind of groups allows me to allocate and run, hey, stick this block of threads running here and stick a different block of threads running something else over here. So I can have multiple processes running. If you need several blocks, I can allocate you to a couple different blocks if you're a really big problem. And then the whole trick for it to be able to handle these efficiently is it'll just kind of move blocks of threads that are ready to go on and off this kind of group of processors. Well, each of these amongst, we're going to be able to run 32 threads on one of these blocks, which means I'm technically going to have 32 little tiny processors inside here. All right, so you can kind of think of it, I'll just do it as kind of this little grid up here. You can just think of those as little tiny lightweight processors that's going on. So each one of these little string things, we can handle 32 of them, boom, they run them nice, away you go. And they all do the same thing. And this is why it's so efficient for things like matrices and whatever, is we've sped these up to do common matrix operations. The most common one we do is, either a SAXP or DAXP. The most common one is SAXP that's out there, although we do allow some DAXPs. Now, you want to get used to what's going on with this, right? These names are telling you a particular operation. This is something you do all the time, but you don't realize it. And this is kind of the most common underscore idea for a vector. Right? This is an abbreviation. This is single. This is double. So it's telling you your precision. Am I dealing with single precision floats or double precision floats? So that's the S or the D. All right? AXPY. This is A times X plus Y. That's what it means. Okay? So when you see AXP, it means A times X plus Y. Okay? Am I doing it in single or double precision? Now the reason why I say this is so common is when you break down most vector operations, if you do a vector times a vector, right? If I'm doing A times, it's, kind of your AX plus Y that goes in. It's going in, if you break it down even to individual elements, you're doing an element of A times an element of X plus some other constant. If I was even just dealing with, let's say, the norm of A, that's going to imagine A as a vector at the moment, right? I'd be doing an element in A times an element of A, adding it into a running sum. So, A times an element in A added into the running sum. So it's amazing how many times you're actually in vectors and matrix operations. Your most basic operation that goes in is A times X plus Y. And it turns out that, you might think, well, why not just do the multiply and addition? Well, it doesn't cost us a lot to do that extra plus Y, but it streams an awful lot of our applications that goes in, so it makes more sense to handle it. That goes in. So this is kind of our most basic operation we do. So you'll see them all over the place that's inside. And so you can think, hey, I'm going to do an awful lot of those, for instance. That's not the only thing it can do, but it really is a common one that we do, and it is a little bit different. First time people see it, they're like, what the heck is that, right? So, that's kind of where, think of it when you're doing them, you're doing a whole bunch of operations such as that one that's going in. I'm going to do 32 of the exact same thing, right? So like here, it's doing, a straight addition. Okay. And I have shared and I have local memory for each of these. Now, shared, all of the threads in here can access shared. Local is each individual one has its own local. Okay? Now, think of local as I might have my own, as an individual thread, I might want to temporarily store some stuff. Like, what if I want to do, I implement this as going temp is equal to A and whatever my index is plus B and whatever my index is, right? Temp would be a local. And then I might say at that point that I want C to be equal to temp. Now, in this particular case, there's not a lot of reason to do that, but what might not be as obvious is if I was doing something like a simple shift to the left. If I want to do this calculation, you can't do this as stated reliably. Because here's the thing, how do you know which one of these finishes first? Right? There's 32 of them going on here. What if I decide, you know, say there's 64 of them running? Which one does it do first? Well, you can't guarantee the order. There's no way. So how do you know that I don't do the +1 first? Which means, since they're out of sequence, you might completely lose all calculation that goes on. How do I guarantee that I don't modify this one and then it propagates? Well, the way that you guarantee that is inside the thread, I say temp is equal to AI plus 1, and then I'm leaving a little space, AI is equal to temp. And then I do double underscore sync threads. Double underscore sync threads means this is a barrier. Everybody must finish what they were doing before they can move on. So what this will do is it'll go out, let's say AIs and globals. This means I'll get a copy of AI into my local memory for each individual thread. I let everybody must finish, so they all get their copy, and then everybody writes their copy. There is now no way that you could actually get confused and separate out, whereas here, sequence would matter, here sequence does not matter. Because I've made sure I've separated them. And so this one forces me, local memory allows me to hold it, and nobody else, each one of us, if each one of us was a thread, right, all of us would have our own local temp. And I don't want you to share temps, because then you would overwrite each other's temp, and everything I was trying to do to protect it would get messed up, right? So you really want this difference between local and shared across. If I were to do this into shared memory, you'd be in deep trouble. Now, shared versus global. You specify global by the keyword double underscore global, double underscore. You specify shared by double underscore shared, double underscore. In general, when you're doing things like the CUDA memory copy, it goes to global. You can specify separately that you want to send it to one versus the other. Oh, I guess I'm getting low on time on here. Maybe we'll finish up a little bit next time as we're going. But you specify that into which one you're going. This one is available to a whole broad range. This is available to each individual as they're going in. This, anything in here, is in, think of it as kind of like registers and level 1 cache, and this is RAM. Right? So this is tremendously faster than this, but there's less of this. So it's almost like you're kind of handling your own caching that's going in. If you have a good reason speed-wise, then you use share. But remember, you don't have a lot of it. So you must use it very wisely, but now you can allocate. So I can control where the memory is to get that speed up. If you've got tons of it, then speed is not the thing, then you go separate. Does that make sense? Awesome. So we'll try to finish this up next time as we go.
Yeah.
Can you hit the button?